Hello and welcome to the latest iFormulate Introduces webinar. Today we'll be looking at the topic of spray drying for formulations, and we're pleased to be running this webinar today in association with the University of Leeds. My name is Jim Bullock from iFormulate, and I'm joined today by Professor David York from the University of Leeds. Since 2012, David has been Chair of Structured Particulate Products in the Department of Chemical Engineering at the University of Leeds and has previously held senior roles in process development and product development at P&G. In today's webinar, I'll be starting off by looking at why we might choose spray drying. Then David will take over with the next few topics: the basic science of spray drying, the hardware of spray drying, some information on material and particle engineering, and I'll finish off with a summary at the end. This webinar will last around 30 minutes and is being recorded, so it will be made available to participants afterwards. If you'd like to ask questions, please use the question box in your GoToWebinar panel, and we will try to answer them at the end of the webinar. During the webinar, we will mute the audience to prevent background noise intruding on the webinar. So the way of asking questions is through the question function. First, a little bit of information about iFormulate. We're a company founded by two experienced industry professionals, and we've just celebrated our third birthday. We bring our own experiences and knowledge gained across many different industries and in varied functional roles. By combining these experiences with the expertise of our associate partners, we're able to assist our clients very effectively. We divide our activities into three different business areas. In iFormulate Consult, we carry out innovation and technology consulting, mainly in formulation technology, for client companies in private sector industry. As iFormulate Strategic, we've carried out and assisted strategic projects in the area of formulation for sector bodies and associations, such as the Knowledge Transfer Network, the National Formulation Centre, and the Royal Society of Chemistry. Under iFormulate Skills, we design, deliver and promote training courses and programs in formulation science and technology, which may appear under our own banner or may be conducted in partnership with third parties. And this webinar is one of our iFormulate Skills activities. There are further details of our current courses on our website. So let's start by taking a look at the subject of drying in general before we start talking in specifics about spray drying. We'll be focusing on water as the solvent today, although the principles apply to all solvents. Water is usually there, of course, due to a previous step in the process, a chemical synthesis or a biological process. So drying in general usually comes at the end of a production process. It means that you are removing a solvent, usually water, as we've said. It can help to reduce transportation costs. It can make your materials more suitable for handling. Drying is conducted to avoid moisture that could lead to corrosion. It's a very effective way of mixing ingredients in the solution or the slurry state so that you end up with consistent products in the dry state. And it can also be used to increase the shelf life of products that might deteriorate if they have moisture present. But of course, you usually have other objectives than simply drying your product. And I normally say that if the only thing you want to do is to dry your product, then you probably don't choose spray drying. But getting a dry product is not the only thing you're trying to do. And some of the other things that you might want from a drying process is to make sure that that process is gentle and doesn't damage a sensitive product. You're obviously looking for good yield and economics. You may be looking for a product that flows well, or perhaps a product that's not dusty. You could be looking for a product with fine particles, or conversely, you might be looking for large particles. You might be interested in the roughness or smoothness of the particles. They might confer some specific product properties on your product. You could be looking for a product with strong particles or indeed weaker particles. And you might be looking to be able to conduct particle engineering. And particle engineering, it's often asked, well, what is particle engineering actually? Well, particle engineering is about understanding what sort of particles you want to make and understanding how to make them. Because the particle structure influences the physical properties of the final product. For example, the flow, the dust, redispersion properties, porosity, controlled release, and so on. So you're designing the particles you want at the end of the process, you're giving the product the desired properties, and you're controlling a number of parameters: particle size, distribution, particle morphology, surface roughness, mechanical strength, internal structure. When it comes to choosing a drying method, you'll find that you have a huge amount of choice. This list of 190, believe it or not, types of dryers comes from a website called Solids Forum. It shows how creative engineers can be in this industry. Fortunately, we won't be going through each of these today, so let's look at just a few of the more common types. Materials can be classified in terms of how fluid they are, so they might be wet solids, or they might be pastes, they might be slurries, or they might be solutions, and they can also be classified in terms of their sensitivity to heat. And they're two parameters actually that are quite important when you come to choose your dryer. So without going in detail through this table here, you can see, for instance, that tray or shelf drying is rather versatile. It has very low losses. It means that your heating is uniform, but it can be a cumbersome and rather slow process involving loading and unloading manually. There's very little opportunity in tray or shelf drying for particle engineering. Rotary drying can be used for pastes and wet solids. Freeze dryers are very good for heat sensitive materials and give you a nice porous redispersible product, but they're rather expensive and complex to control, and again you have little opportunity for particle engineering. Drum dryers are very good if you've got a viscous feed. They're relatively simple and to operate and rapid, but there is some expertise required in controlling film thickness, and there can be a maintenance requirement as well. Microwave drying is sometimes popular for drying sensitive materials. It can be used for bulk materials, viscous materials, and it's a rapid process. When you come to larger batches, it's trickier to get microwave drying operating, and again there's little opportunity for particle engineering. Vacuum drying gives you low risk of oxidation and heat damage, and can be used for small batches, but for large batches again it's tricky to dry large batches in a large scale vacuum, and again controlling and particle engineering can be a challenge here. Fluid bed drying is another popular process. High drying rate, uniform drying is possible from the particle surface. It gives you really nice free flowing particles, but those particles have to be at least 250 microns in size normally to form a controllable fluid bed. And there is a risk that the process may break down your particles and form a dust. So let's just run through some of those other reasons that you might choose spray drying. And here are some application examples that show that spray drying is versatile in coping with a wide range of materials, but also the ability to tune the resulting powder properties. Water removal, carrying out chemical reactions, the speed and ability to control temperature, all very important reasons. So spray drying can be used for thermally sensitive biological materials and food, for instance. It can be used to mix ingredients, to formulate products in situ with excellent uniformity of mixing. And again, its ability to control particle size and structure from solid particles through to highly porous spheres and even microencapsulates demonstrates that it's a very versatile process. And we just listed here a few of the examples, but you can see in terms of scale, you might be drying something on the sub-gram level in pharmaceuticals, or on the many hundreds of ton scale in products such as foodstuffs and detergents. So huge range of reasons you might use it and a huge range of potential applications. So let's just run, before I hand over to David, let's just run briefly through the pros and cons of spray drying. Very rapid drying through a large surface area, good contact, high mass transfer, high heat transfer. It's a semi-continuous process, a single stage, reducing the handling that you need. It's flexible. You can use, if you wish, non-aqueous solvents and inert atmospheres. Heat is used in the main to vaporize the solvent and not to heat the solid product. So it's very good for sensitive materials. Particles are genuinely uniform and they disperse and flow well. And as we mentioned already, there's a high potential for particle engineering, which David will touch on in more detail. On the disadvantages side, well, the equipment can be complex and expensive, and it can be large for larger scale products. You need the material to be pumpable and atomizable, otherwise it won't go through the nozzle in the first place. And you need to be able to understand and control each stage to get the best out of your process. And there is the fact that occasionally what you get in the lab may look rather different from what you get in production scale, which can be a challenge. So now what I'm going to do is to hand over to David, who will carry on from this point. David.
Thanks, Jim, and hello from Leeds. We talk about particle engineering nowadays, and this is no more applicable than in spray drying, especially now our understanding of the scientific principles of the process are so well understood and our measurement techniques have improved dramatically. There are so many benefits since you have so many factors you can change to get the effect you want. There are a few more downsides to consider also. It does require a number of equipment items, not least a system for separating dust from the hot, humid air, and it can be capitally very expensive on the large scale. It needs a starting material, as Jim mentioned, to be fluid enough to atomize. So liquids tend to be at least 40% by weight, often above 60%, in order to be able to pump and atomize. And like any operation, being able to scale up from the bench to full-scale plant is not easy either, and this is very true for any particulate process. This becomes more challenging as the particle size increases in general. So what about the basic science? Drying happens at the interface between the droplet and the hot air. Therefore, surface area is critical to the speed at which this can happen, and this is why spray drying is so fast. Atomizing the liquid into small droplets rapidly increases the amount of surface to dry, and so speeds up the process. This increase in surface area also leads to an increase in surface energy because of surface tension. So you need to put some energy into the system to do this, and that's why atomization is so important in this case as well. On atomization then, fortunately this is relatively easy to do, and anyone who's watered the garden will have experienced the process. The energy put into the liquid breaks it up into thin films. These films are very unstable and consequently break into fine particles or droplets. There are three common ways of doing that which are shown here. And because this is not an exact science, and it's very old science, there are as many ways of designing atomizers as there are spray dryer operations. Whilst there is some control on the size of the droplets, you get a wide variation around the mean, since the breakup of the film is random. And you can see here there are three basic types: the pressure nozzle, the air-assisted pressure nozzle, where the energy for atomizing comes from pressurized air, and then there's the centrifugal motion of the spinning disc. There are specialized atomizers which I've listed at the bottom as a couple of examples. These give you a much tighter control, and it's possible to get a uniform droplet size with virtually no variation. But they're currently more expensive to operate and have restrictions on the viscosity that they can handle as well as the throughput. As you would expect, the viscosity of the liquid has an important impact on how easily it can be atomized. And here is the first area where the formulation is a key factor, something you can control, hopefully. However, we need to be careful in how we look at viscosity, since this property can be highly dependent upon the shear rate. Some liquids are very viscous at normal shear, but since the shear rate in a nozzle is very high, the viscosity can reduce enough to allow atomization. A good example is detergent slurries. These start out looking like thick porridge, but at the shear rates inside the nozzle, they are relatively easy to atomize. On the subject of slurries, it's worth pointing out the obvious one, that if you've got a slurry with particles in it, the nozzle diameter needs to be big enough not to get blocked by the particles. And a good rule of thumb here is to have the nozzle diameter at least 8 times larger than that of the biggest particle. All processes need a driving force to work. In our case, it is the difference between the humidity of the surface of the atomized droplet and the amount of water the air can take up. Once the air becomes saturated, no further drying can take place. After all, you cannot dry washing in the rain. One of the most important factors that impact this is air temperature. As this increases the amount of water the air can take up before it becomes saturated. As you can see, between 0 and 95, the amount of water that the air can take up increases by a factor of over 1,000. The other impact of temperature is that it drives energy into the droplet and increases the amount of water available with sufficient energy to turn to steam and to move into the surrounding air, so increasing the rate of drying. So let's look at a typical droplet and see what happens during its experience in the tower. Moving from left to right, it starts with the water content even from inside to out, and I've used these colours to try and demonstrate that. So at the start, typically the surface and the inside is saturated. As long as the surface is saturated, the rate of drying is almost constant, assuming there's sufficient capacity in the air. This happens as long as the water from inside the droplet gets to the surface fast enough to keep the surface saturated. This evaporation needs energy, which comes from the surrounding hot air. And so the droplet temperature is kept usually at a much lower temperature than the surrounding air, because the evaporation is taking away the energy from the hot air. This is an advantage for spray drying, particularly for sensitive materials. Much like spraying yourself with water droplets keeps you cool in hot weather, so the evaporation keeps the droplet cool until it starts to lose its speed at which it can evaporate water. Over time, the surface water reduces as the transfer of water from the center slows down, and the droplet water content in general reduces. Then the surface starts to dry out and crust, and it is no longer saturated, and so the drying rate reduces. Water is not moving from the inside to the surface of the droplet fast enough to cope with that is lost through drying. Since this rate of transfer of water takes time, the longer the distance it has to move from the center to the outside, the slower it takes to get to the surface. Thus, bigger droplets will have a bigger difference in water content between the core and the surface. What happens next is very formulation dependent. For those materials that form strong bonds with water, such as surfactants and starches, etc. The water moves much slowly through the droplet to get to the surface, and the temperature then of the surface and the droplet starts to rise. Indeed, in extreme cases, the water transfer becomes so low it cannot evaporate fast enough to cool the granule down, and the heat coming in from the outside air will eventually turn the water inside to steam, and this can cause rapid expansion and puffing and high porosity, much like baking a cake, although if the formulation is too brittle, then you can get shattering as well. Why is droplet size so important? Well, as mentioned, large droplet sizes can give rise to very large water gradients, depending on formulation. Another important factor, though, is that they also take a bit longer to dry, as they fall much faster, and they fall much faster due to gravity. So their residence time in the tower tends to be much lower. So you have a greater need to dry and less time to dry. So there's a natural limit to the droplet size that you can use in a spray drying tower. However, if you want to have bigger particles, you can compensate for this by making much smaller droplets and then getting those to collide at the appropriate time within the tower by controlling the airflow rate and where you put the nozzles, and get them to stick together in the tower. And the example here you can see is a typical detergent particle where those smaller droplets are stuck together, and you end up with a particle somewhere in the region of 400 to 600 microns. So what about the hardware? Well, there are many variations on a theme, just like in Jim's initial slide on drying types. But the basic principles are to feed a liquid into a vertical tower at the top. Then you atomize it and let gravity take it down. The usual configuration is co-current, so the hot air comes in at the top also. Here both particles and hot humid air exit at the bottom. Big dry particles can be readily separated from the hot air and come out through a valve marked product. If the product is finer, then everything goes into the cyclone, and that's where the first separation takes place. And then for the very fine dusty particles that still haven't been collected, then it's typical to go through a bag filter before venting the hot humid air to atmosphere. If you want to buy a spray dryer, there's an awful lot of choice. There are two basic ways of operating. You've already seen the co-current design, where liquid and hot air enter the top together and come out the bottom together. The other basic design is countercurrent, where the hot air comes in at the bottom and runs counter to the droplets that come in from the top. So you get separation of the air comes out the top and the product comes out the bottom. The cyclones and the bag filters then are on the top of the tower. Then you can have short and fat designs. These are ideal for spinning disc atomizers, because if you can imagine it, the centrifugal force on the disc throws the droplets sideways for a while before gravity takes over. And so they tend to need a wider design to prevent the droplets hitting the wall before they're dried. Because one of the cardinal sins of spray drying is to have wet droplets hitting the wall and drying on the wall and causing makeup. Not a good idea. The other style is tall and thin. These give you long residence times, and there's lots of mixes in between. This chart shows the general uses and impact of each type, though I have to emphasize that this is a very general slide. Then, depending on the formulation, the droplet size, the air temperature, and the moisture content you can move from solid spheres to highly porous particles, donuts to deflated footballs, and a host of other shapes and sizes depending on your needs and also the formulation. That's why it's so important to work out what your desired particle properties need to be at the first, and then work backwards through the process to define your mix conditions and your process conditions and what atomizer that you want. It's much better to do it that way than to try and force fit forwards. And finally, as an example of a more complex engineered structure, you can also encapsulate particularly volatile materials such as oils and flavors via spray drying. This is a very cost-effective approach compared to standard encapsulation processes. Basically, you form an emulsion with very fine droplets of the oil stabilized by particles of starch or proteins such as milk, and then you atomize the liquid to form droplets. So you've got droplets inside of droplets. As the droplets dry, the protein or starch particles, which are not that soluble, migrate to the surface of the oil interface, and as the particle heats up, the starch or the protein will start to sinter. And it's very important then that you choose your starch or protein with the right properties to be able to do this. They sinter and then they form a solid wall and keep the oil from escaping as it heats up. The result is a sort of matrix particle with filler around microencapsulated oil. So that's just an example of a bit more complex particle engineering that you can achieve with spray drying.
Thank you, David. So let's summarize briefly what we've learned today. So spray drying is a highly flexible process, as David's shown you. It's very cost effective. It can be used to fine-tune the material and particle properties that you want in your final product. The industrial applications are very varied, but no matter which application you're involved in, no matter what the scale, the basic science is the same. So the same science applies whether you're spray drying biopharma actives, very small volumes, or whether you're drying large volumes of detergents, for instance. And three factors really are critical here: the equipment design, the materials properties or the formulation, and the process conditions. And these interact with each other and influence each other, as we've kind of depicted in that triangle there. It can be a complex process, but don't panic. Spray drying has a scientific basis and it can be made understandable. And we have just enough time really now to tell you a little bit more about how you could learn more about spray drying. And between the 12th and the 14th of April will be the next spray drying and atomization of formulations course at the University of Leeds. It's being run for the third time and has grown every year. We'll be covering fundamental principles. We'll be covering practical applications and industrial case studies, and includes laboratory demonstrations as well. So the subjects you've heard about today will be gone into in a great deal more depth, and there'll be opportunities to speak to expert speakers from industry and academia. The 2015 event was sold out, so we do recommend, if you're interested, to book early, although attendees of this webinar can make use of the early bird £50 early bird discount for a week longer until the 4th of March. So 12th to the 14th of April, we've got speakers from industry and academia, and you can see some of the names there on that slide. You see a very broad range of industries and academics represented. And the course has been extended this year with extra material. At this point, I'd like to, first of all, provide opportunities for questions, and thank you for your attention today, and thank you, David, again for your contribution. It's now time for questions. We'll keep you muted, but this is the opportunity to use the GoToWebinar chat function or the question box here. If we don't have time to answer your question today, or if there are any follow-up questions that you may have, you can see the email address to get in touch with us here. We'll be providing you with details of how to access a recording of the webinar, and you can see some details about upcoming webinars and other events there as well. So you'll get a chance to see a recording as well. So we've now got an opportunity for slides, for questions. I've got one question coming through here, and I think we've probably only got time for one. So David, I'm just expanding the question box here. If you hold on a second. Yeah, David, it's probably a question for you. What about drying a water in oil emulsion? Never thought of that one myself. I don't know if you've got any interesting ideas on that one.
That's a tough one because typically it depends on the oil, and it depends why you want to dry it. Because if you've got an emulsion of water inside the oil, then presumably there's something inside the water phase that you want to generate an emulsion. I think the challenge is really it's too difficult to give a simple answer. It really depends on what oil you've got and what you want to achieve. Typically, though, getting water out of the internal phase through the oil phase and dry will become very difficult. And I assume by the question you're trying to dry the water rather than the oil.
Thank you.
So if you send a follow-up note as to exactly what you're trying to do, then we can probably give you a much better answer. I apologise for not being able to give you a direct answer.
Next question has probably got a range on the answer. What's the cost per kilogram? And the answer is it depends, I'm sure, but typical range?
It depends on the amount of moisture. The main cost is the drying stage. That is both the energy that's required to evaporate the water, and the other factor here is that the capital depreciation over the production rate can have a big effect. So people tend to minimize the amount of moisture they put into their system if they can, in order to reduce the energy consumption, but also to get a much higher throughput for the same piece of equipment. Now that obviously refers to the food and chemical industry. If you're talking about the pharma industry, where you're only trying to produce a number of kilos per day or per week, then that's less important. It is one of the most cost-effective ways, though, of drying, and particularly on a large scale. So it would, and it's also very efficient. So as you can imagine, you can get over 100 tons per hour through a spray drying tower. So you're talking of probably less than $1 a kilo of product, but all that depends on how easy it is to dry and how much moisture there is in the system.
Just probably time, thank you Dave, for one more question, and that's once the water's gone from the particle during the process, what's inside the process? Air?
Well, the first thing to say is that sometimes it's acceptable not to take all the water out of the particle. Sometimes it's acceptable to have a small amount of residual water inside the particle. It doesn't affect the free flowing or stability of the particle. But yes, once the water's gone, nature doesn't like a vacuum, and there'll be air inside. So, and again, how much air depends on the process conditions. If you have a highly porous structure, then there's going to be a lot of air. If you dry it in a different set of conditions, you can have a nice solid particle, and the droplet actually shrinks as it dries, and as the water goes out. So you can actually form fairly low porous particles as well.
Okay, so thanks very much, Dave. We've gone slightly over time, so that's all we've got time for. If you do have any follow-up questions, like we say, there's the email address in front of you there. Thanks very much for your attention. We hope to see you again at another one of our webinars, and also potentially in Leeds at the spray drying course in April. So thank you again to David York, and thank you for attending today.